So we are busy discussing the Kraft pulping cycle, which consists of cooking of wood chips. The black liquor then goes to an evaporation plant, and after that the black liquor goes via the Kraft recovery cycle, and in the end we generate our cooking liquor. So in this video we're basically just going to focus on this area of our cooking liquor and the cooking itself. Later on we will talk about the evaporation. The white liquor or our cooking liquor contains NOH and Na2S, and these are added as so-called white liquor either to an impregnation vessel or to the digester directly. As you will see in your technology course, sometimes the impregnation is actually happening at the top of the digester, and in the digester these two chemicals will react with wood components such as the lignin, cellulose and hemicellulose, and in the process they are converted to Na2CO3, and the Na2S is converted to Na2SO4, and some other components in the wood are saponified. And these black liquors are then sent to the evaporation plant, but we will not focus on that right now. Let's start summarizing the overall reaction, Kraft reaction in the digester. Our white liquor chemicals, NOH and Na2S, dissociate to form OH- and SH-. These are the active ions that will react with the lignin in our wood. And obviously the first product is the pulp or the separated fibers, and then black liquor. In this black liquor we will have dissolved lignin, some saponified components that were saponified during the Kraft cooking process, and then our cooking chemicals that would have been converted to Na2CO3 and Na2SO4. In the table we can see the relative amounts that we start with, the NOH and the Na2S in the black liquor, and then the conversion to either Na2CO3 or Na2SO4. Okay, so let us now consider the Kraft reaction. We have seen this graph before where we have shown the change in the alkali concentration as the reaction progresses, and then we've also seen how lignin are dissolved and how the amount of lignin that's still left on the fiber changes as the reaction progresses. So let us now divide this reaction into different stages. The first stage is the so-called impregnation stage, and you can see in that stage there is very little reaction happening and very little, if any, lignin is dissolved because the temperature is very low. In the next phase, the initial cooking phase, there's a little bit of reaction happening as the temperature is increasing, some of the lignin is dissolved. And then the bulk cooking phase, that is when the main reaction is happening, the rate of reaction is high, the temperature is high, and we can see the decrease in the alkali concentration and the amount of lignin that is still on the fiber. And then finally we have a so-called residual cooking phase, and in this phase there's a little bit of lignin being dissolved, but not much reaction, and we will see later if any reactions is actually reactions with our carbohydrates that will happen at this stage. So the next concept that we have to define is the so-called alkali consumption, and this is indicated by this purplish blue line. And what we mean by that is the actual absorption of the alkali and the cooking liquor chemicals into the wood chips, into the lumens, the actual penetration of the liquors through the cell wall. Okay, so this does not mean necessarily reaction. It just means that the alkali is being absorbed by the wood. So therefore we find that during the initial impregnation stage we have 30 to 40% of our alkali being consumed, and most of that is actually then about the hemicellulose that will be degraded in that stage. In the initial cooking stage we still have another 30 to 40% of the alkali that is consumed, but during the bulk cooking phase we actually have very little alkali that is consumed. But as we can see and we have discussed, during this stage is now when the chemicals is already in the wood chips, now it can react with the lignin, and that is when we have the fast reaction at the high temperatures during the cook. And then during the residual phase we might have a slight increase in the alkali consumed. Okay, so in total we find that we consume about 150 kilograms of NOH per ton of wood, and that this OHs are then actually bonded to the dissolved lignin. However, for the sulfurity, interestingly, we find that although they have taken part in the reaction, they are not consumed. They do not stay with the lignin, but is released back into the solution, and eventually it will end up as sodium sulfate. Okay, so what is the implications for the mole of this? First of all, although we say that the sulfites are not consumed, we have to remember that there is a loss of some of the sulfur compounds due to the formation of things like mercaptans, and that this will be removed from the digester, and that results that we have a change in the balance between the amount of SH minuses and OH minuses, and in total about 5 to 10 kilograms of sulfur components is lost per ton of wood that is cooked. And this means that if we now later on will be talking about the recovery of our white liquor chemicals, is that we will now have to restore this balance between the amount of SH and OH, and that means that we will have to try and regain the correct percentage of sulfurity